So, let us continue the discussion on compressible flow. We have started with one dimensional steady compressible flow equations, and then from there we move to the normal shock relation, and we have then towards the end of the previous discussion we have actually looked at when there is a flow is isentropic, what happens to the stagnation properties, and when the flow is actually across a normal shock wave, then what happens to the stagnation properties. So, that is what we have already discussed. Now, moving ahead, we will talk about now the oblique shock. So, this is a kind of shock. When we looked at the normal shock, our shock was always perpendicular to the flow field, but when we talk about oblique shock, so one can always say that normal shock is a special case of the general inclined one, because when the shock is inclined to a object, let us say in two dimensional flow, then that is what I mean. Obviously, the flow has to be supersonic, and for example, let us say if you have a kind of base like this, and then you have you have kind of a base like this, and then it goes like that. So, there would be a inclined shock here. This is a inclined shock, and there is an angle to that. This is called beta, and there would be some angle which is delta max. So, let us say when this is an kind of, this is how the flow comes in, this is an wedge shape kind of geometry, and this is in two dimensional flow. So, when the flow comes in, a plane attached shock wave may occur here, and this is with an angle, some angle beta, and the flow Mach number and the wedge angle together. So, this is the delta is so called the wedge angle. So, this kind of shock is called the oblique shock, and it is a generally inclined one. And if you think about when we say that normal shock is a special case, then that is a perpendicular to the flow field obviously. So, when a supersonic flow encounters a concave corner with an angle delta, there are two possibilities of attached or detached shock, like we can have. So, this flow is also supersonic here. Now, I can have, let us say, configuration like this, let us say like this, and the flow here is inclined there. Then we can have a shock like this. This is the one which is called attached. So, this is another example of oblique shock which is attached, or we can have another configuration like this, when the shock could be like this. Still the Mach number incoming flow is like this. This is called the detached. So, that means when the supersonic flow, you have this kind of object sitting in the flow field, Then the upstream flow, when it is supersonic, then either you can have this kind of attached shock, either you can have discharge shock, but these are not obviously perpendicular to the flow field. So, these are all can be clubbed together and called as an sort of an oblique shock. Now, then there could be some other possibilities, like another possibility could be like this one, the wedge shape kind of situation, where the shock could be like this. Again the flow is supersonic, or I could have a situation like this, when the flow could be like this. So, this is again one can say this is attached oblique shock, this is so called detached oblique shock. Okay. So, these are the possibilities which may occur there. Now, when the deflection angle, there is a maximum deflection angle which is called the delta max. So, delta max is the maximum deflection angle. So, this is there is always exist a maximum deflection angle, which is obviously one can say this is associated with Mach number. It is not that it is irrespective of the Mach number, because depending on the Mach number this deflection angle could be different. When the deflection angle, let us say delta max, exceeds, then a detached shock forms which is a curved waveform. So, this has a, this is called the bow like pattern or bow shock. This is called bow shock or bow like shock which is formed. So, in this case the delta is greater than delta max. That means the deflection angle which is here, this is the delta, the deflection angle is greater than delta max. So, that time you can have this kind of pattern, or when it is delta less than delta max, they will remain attached. Okay. So, behind this bow shock or curved shock, so we can find all shock solutions. So, this is the upstream of it and this point would be the downstream of it. So, we can find all possible shock solution associated with the initial Mach number m1. So, if this side is m1 and we can find m2 and all sort of things here. Now, at the center of normal shock, at the center a normal shock also exists. When there is a bow shock, there is a center could be a normal shock with subsonic flow result. As the wave front curves around, the shock angle actually decreases continually with a resultant decrease in the shock strength. So, with this the strength also decreases. Eventually, one reach a point where supersonic flow exists after the shock front. Now, this oblique shock, there are different kind of oblique shocks which are preferred in this all engineering applications compared to normal shock. The one of the we can associate it with these oblique shock relations as we go on discussing about that, but there is an fact that combination of oblique shocks is more favorable for post shock conditions, like so combination of oblique shock which is preferred because the post shock temperature to reduce or have lower post shock temperature and pressure. So, these are important. Now, this combination is more preferred compared to the normal shock, and the reason being that across a normal shock flow will become always subsonic. So, the change in properties are quite drastic, but as we go in the discussion we can see that the behind the oblique shock the flow still could be supersonic or subsonic depending on the situation. So, this combination one can think about, this is a good combination for design of supersonic aircraft. So, especially the intake portion, which are wedge shaped to compress the air into the combustion chamber while minimizing the thermodynamical losses. But early days this kind of supersonic jet engines which were designed using compression form of a single normal shock, but when you use a single normal shock, this has some limits of operation, because the behind the shock the flow is going to be immediately subsonic and which has drastic change in properties. Now, typical Mach number, so one can see these things, the wedge shape kind of patterns are used in like F-14 fighter aircraft, which has maximum Mach number of roughly 2.3, something like that, 3.5 or something. Now for analyzing oblique shock, let us consider a particular, let us take this wedge kind of pattern, and let us say this is, then this would be the shock sitting there, this is beta, this is delta. So, the flow comes in here, this is the velocity triangle for that. So, this is Mach number 1, this is beta, this is M1n, 1t, that is a tangential component of the Mach number, one is normal component, one is tangential component, and then here we will have the velocity triangle like this. So, this is M2, this angle is beta minus delta, this is M2t, this is M2n. So, we take this figure where the delta is the flow deflection angle, okay, and beta is the shock inclination angle, or rather one can say the shock has the generated shock inclined to at angle beta to the flow direction. One can say that, or can be said that a shock generated inclined angle to the flow direction. So, that is what one can say. Now, the flow approaches with a velocity v1, so this is the approach velocity, or one can say upstream velocity ahead of the shock, and it turned through a angle delta, it passes through the shock leaving with a velocity v2. So, this is the downstream velocity downstream of the shock. So, obviously, this would be associated, the v1 is associated with Mach number 1, this is Mach number 2, and there will be an angle beta minus delta which is respect to the shock. The inlet and exit velocities can be decomposed in the normal component and the tangential component, where similarly we can have the velocity. So, the tangential, so like the Mach number, we can have the similarly velocity components. The tangential velocity components upstream and downstream are equal. So, that means V 1 t would be V 2 t, which means V 1 n is supersonic and V 2 n is subsonic, but even that V 2 is supersonic at the downstream. So, we can write this tangential component to be equal, and using this Mach number relationship. Now, what one can write now, that V 1 t is V 1 cos beta, V 1 n would be V 1 sin beta, and then M 1 n is M 1 sin beta, which would be greater than 1, and you have one tangential component which is M 1 cos beta, and M 1 is supersonic. So, which is greater than 1. So, these are the using the velocity triangle one can easily write this. Similarly, at the downstream location V 2 t would be V 2 cos beta minus delta, V 2 normal component would be V 2 sin beta minus delta. So, normal component of the Mach number would be M 2 sin beta minus delta, which is less than 1, and M 2 t, which is M 2 cos beta minus delta, and M 2 is also supersonic. Now, since the oblique shock can be treated as a normal shock, where we have an upstream Mach number, like now since oblique shock can be treated as normal shock, which having a Mach number upstream is 1 n is M 1. So, the normal is sin beta, and a tangential component like M 1 cos beta. So, then if we treat like that, like these components here, we treat them as an normal shock, and then we can use all the, then using the normal shock relation, what we can write, that we can write some relationship between delta m, m 1 beta, m 1 like that, which gives us that tan delta would be 2 cot beta, m 1 square sin square beta minus 1 gamma plus 1 m 1 square minus 2 m 1 square sin square beta minus 1. Let us say if you consider a value of gamma which is 7/4, then tan delta become 5 m 1 square sin 2 beta minus 2 cot beta 10 plus m 1 square 7 plus 5 cos 2 beta. So, we get now what happens to the normal components. So, the normal components would be m2n square is gamma minus 1 m1n square plus 2 by 2 gamma m1n square minus gamma minus 1. Similarly, so what we can write m2 square sin square beta minus delta would be gamma minus 1 m1 square into sin square beta plus 2 gamma m1 square sin square beta minus gamma minus 1. Now, if we say for gamma is 7 by 4, what we get m2 square equals to 36 m1 4 sin square beta minus 5 m1 square sin square beta minus 1 into 7 m1 square sin beta plus 5, where 7 m1 square sin square beta minus 1 m1 square sin square beta plus 5, and we get P2 by P1, which is 2 gamma m1 square sin square beta minus gamma minus 1 gamma plus 1. So, when we use for this case also, for gamma is 7 by 4, this P2 by P1 becomes 7 by 7 m1 square sin square beta minus 1 by 6. Similarly, T2 by T1 we get 2 gamma m1 square sin square beta minus gamma minus 1 gamma minus 1 m1 square sin square beta plus 2. So, which is gamma plus 1 m1 sin square beta. Similarly, for gamma equals to 7 by 4, this T2 by T1 becomes 7 m1 square sin square beta minus 1 m1 square sin square beta plus 5. So, which is 36 m1 square sin square beta. Now, the other quantity which could be also written like the density ratio, rho 2 by rho 1 would be gamma plus 1 m1 square sin square beta 2 plus gamma minus 1 m1 square sin square beta. For 7 by 4, this rho 2 by rho 1 becomes 6 m1 square sin square beta by m1 square sin square beta plus 5. Okay. So, we can also write down the relationship for the stagnation condition, write P2 naught by P1, which is like you have gamma plus 1. This one can find or look at the detailed of these calculations in any of the compressible flow book. So, just I am just giving it or going through these things quickly, because this is not, these are all required, but not the part of our detailed discussion of this course. So, So, same thing for 7 by 4 gamma, you get P naught 2 by P naught 1, which would be 6 m1 square sin square beta by m1 square 7 by 2 and sin square beta minus 1 5 by 2. So, these are the different relationship between temperature ratio, pressure ratio, density ratio and stagnation condition. So, this actually one can have these relations, or there could be a nice diagram what can happen between M1 beta delta, using that where you can get a diagram of that kind. For example, I am just, if I draw it qualitatively, so this is M1 and this side is beta, which starts from 10, 20, 30, 40, 60, 70, 80 and so on, and this side 1, 1.5, 2, 2.5, 3, 3.5 like that. So, you have kind of, again as I said, so you get this kind of curve like that. So, these are for different increasing delta, and this is beta and this is M1. So, this is called the delta beta Mach number relationship plot, which is quite important because one can use this graph to find out the conditions for a particular Mach number, what could be the deflection angle, what could be the other angle. Similarly, you can have the another plot which can also give you the idea about the downstream condition. So, if I plot that, which goes from 0, 5, 10, 15, 20, 30, 35 and so on, this is the delta, and this side it would be 1 minus Mach number inverse. So, this is called Mach number parameter. So, you get this goes from minus 1.75, 1.5, 1.25, 1.75, 0.5, 0.25 like that. So, qualitatively you get curves like this. So, these are again, this direction is increasing M1. So, instead of using those complicated equations, one can use these two curves, where when you have the upstream Mach number, from there use for a given value of delta or wedge angle, you can find out the beta, and then when you, or rather for beta, given a beta and M1, you can find out delta, either of them, and with that when you come to the downstream of the system, where you need to find out the Mach number at the back of the these things like the downstream of the shock, then this is a Mach number parameter called the Mach number parameter, which is not directly M2, which is written as 1 minus M2 1 by M2, and then the qualitative plot would look like this. I would suggest you guys should look at the book properly to see this diagram with proper numbers, because these are again, repeatedly I have been mentioning this. These are qualitative plot which I am trying to draw just to give you an idea how they look like, what are these parameters all about, and how one can find out the details. Coming back to that, once you identified, so this is the upstream situation which you can get, and once you find out either beta or delta depending on Mach number, using that, here is a relationship between delta M1 and M2. So, this is M2, M1 and delta relationship curve. So, you can use that and actually find out the Mach number downstream of the shock. So, this is how the oblique shock relations can be used. It not necessarily one has to sort of mag up those or keep remembering those equations like these complicated equations. This is not expected. In I mean, these are the handbooks or tables which are available for oblique shock relations, or this kind of plots or the graph which are very handy for designers to use this relationship to find out upstream and downstream properties. And once you find out the Mach number, then rest of the things can be followed very easily. And so, that is what will pretty much want to just touch upon the discussion on oblique shock. We will stop here and continue on the other portion in the next class.